Research is rarely a straight line. When human experts investigate a complex topic, every new discovery dynamically alters the path forward, creating sudden dead ends and revealing unexpected leads that require exploration in real time. Standard AI pipelines handle information retrieval through Retrieval Augmented Generation, or RAG. RAG matches a user's prompt to a static set of text chunks from a database. This model hits a hard boundary because it cannot adapt its search based on discoveries during the process. Even when equipped with search tools, a single AI agent operating in a loop hits a structural wall when attempting deep, open-ended research. A single agent must process every search sequentially, reading a document, formulating a new query, and repeating the cycle. This is painfully slow, and it rapidly consumes the model's context window, the memory limit determining how much text it can process at once, until the system loses the original plan. Reasoning across vast data sets is a problem of data compression. Linear AI pipelines lack the architecture to distill scattered findings into a coherent answer in real time. Anthropic tested this by running a multi-agent system against their standalone Claude Opus 4 model. On internal research evaluations, the multi-agent architecture outperformed the single agent by 90.2%. This scatter plot shows the browse comp evaluation. 80% of performance variance is explained by token expenditure. Distributing research across agents, each with separate context windows, bypasses single model limits. The system spends a larger computational budget on the same problem. Simply upgrading to a more capable base model does not solve these logic tasks. Even the most intelligent models fail when the sheer volume of data exceeds their individual processing capacity. Reliable multi-agent systems are built on orchestration and state management, moving past the limitations of simple prompt-level instructions. While adding more agents provides the scale required for autonomous work, it introduces a new engineering hurdle: the risk of compounding coordination errors. In an orchestrator worker pattern, a central lead researcher node maps a strategy to memory and spawns specialized subagents. These subagents run simultaneously, pinning databases in parallel to extract facts. They return only relevant tokens to the lead, who synthesizes a report for a final citation agent. The citation agent has a singular task: mapping every claim in the report precisely back to the original source documents gathered by the subagents. Decoupling synthesis from attribution is the key to maintaining factual integrity within a sprawling multi-agent network. Node architecture is only the beginning. Without precise behavioral programming, parallel agents can spiral completely out of control, endlessly scouring the web for non-existent sources or spawning dozens of workers for simple questions. Early testing showed that vague instructions caused subagents to misinterpret their tasks, leading to redundant searches that wasted time and tokens. Without clear delegation on the semiconductor shortage, multiple subagents redundantly investigated the 2021 automotive chip crisis, completely missing the current 2025 supply chains. The fix requires rigid prompt engineering for delegation. Every subagent must receive explicit task boundaries, a list of required sources, and a specific output format. Anthropic embeds scaling rules into the lead agent's instructions. A simple fact-finding mission uses one agent, while complex research triggers 10 or more specialized workers with clearly divided labor. In this framework, prompt engineering becomes a method of system resource allocation, preventing the network from overinvesting in simple queries. Another failure point is the agent tool interface. If a tool's description is vague, an agent will apply the wrong parameters, leading to hallucinations or infinite error loops. Agents must follow strict usage heuristics. The system forces them to execute broad web searches first, before allowing them to drill into specialized, narrow databases. To refine these interfaces, Anthropic used an LLM to test and rewrite flawed tool descriptions. This automated iteration cycle reduced task completion time by 40%, avoiding common mistakes. The lead researcher uses an extended thinking reasoning buffer to plan its next move, assessing tools and defining subagent roles. Subagents also use interleaved thinking, pausing to evaluate data quality and identify gaps before firing their next parallel query. Guiding these intermediate reasoning steps ensures that parallel tool calling is both fast and accurate. High performance comes with a cost. Multi-agent networks consume roughly 15 times more tokens than chats. This bottleneck overwhelms the lead agent's context window with raw data. The solution is bypassing the coordinator. Subagents output structure ADA blocks directly to an external file system, sending only a lightweight reference link back to the lead researcher. This artifact system preserves the lead agent's context window for high-level synthesis rather than raw storage. Persistent memory checkpoints allow the system to resume from a failure point without restarting the entire expensive research run. Managing long-horizon AI tasks is ultimately an exercise in persistent state management and intelligent context offloading. This leads to the final challenge: evaluation. Multi-agent systems are non-deterministic. Identical queries might take entirely different paths and arrive at the same correct answer. Because many valid routes exist, judging based on a prescribed sequence falsely flags correct logic as a failure. Instead, engineers rely on end-state evaluation. An LLM acts as a judge to verify the final outcome rather than the specific steps taken to get there. The judge applies a rubric that measures factual accuracy against the retrieved sources, the precision of citation mapping, and the overall quality of the sources used. Human evaluation remains essential to catch subtle emergent behaviors. Humans discovered agents often preferred highly ranked SEO content farms over authoritative but less visible academic PDFs. Reliability in production requires abandoning rigid procedural checks in favor of rigorous final state verification. In a prototype, these systems run in a pristine environment. In production, a single tool failure or a bad website scrape can cascade into unpredictable trajectories that derail the entire network. Stability in these systems results from robust orchestration frameworks rather than the refinement of individual prompts. Scaling the capability of collective AI intelligence depends on mastering the mechanics of division of labor, memory persistence, and end-state validation.